You know, our planet is never really still. I mean, one day a hillside is covered in forest, and the next it's a construction site. Coastlines are always shifting, cities are expanding, and entire landscapes can be totally rewritten in the blink of an eye by fires, floods, or earthquakes.
And these changes, they're not just dramatic, they are unbelievably expensive. This number right here, that's the estimated direct economic damage from natural disasters in just 24 years, from 1980 to 2004. Yeah, that's a trillion with a T.
So this brings up a massive question. With so much happening everywhere all the time, how do we possibly monitor it all? How do we tell the difference between a really significant event, like an illegal logging operation starting up, and all the normal seasonal background noise?
Okay, let's get into it, because scientists have developed this incredibly powerful new solution. It's an algorithm with a pretty cool name, and it's basically designed to be our planet's sleepless watchdog.
It's called COLD, which, stands for Continuous Monitoring of Land Disturbance. And its whole job, its fundamental purpose, is to sift through decades of satellite imagery and automatically spot all kinds of land disturbances as new pictures are beamed down from space.
And this is where things get really interesting, because COLD is a huge leap forward. See, its predecessor, an algorithm called CCDC, it was pretty good at seeing a change in what's called land cover, like say a forest turning into a city. But COLD is way more sophisticated. It's built to detect the disturbance event itself, the fire, the insect infestation, the actual act of logging that causes the change. It's really the difference between seeing the final scar and witnessing the moment the wound actually happened.
So how on earth do you teach an algorithm to see something as subtle as a beetle infestation from orbit? Well, let's break down the genius behind how this thing actually works.
The whole process is actually a lot like your credit card's fraud detection system. First, for every single 30-meter square of land on the planet, the algorithm studies its entire history to learn its normal seasonal rhythm, its unique heartbeat, if you will. Then, as new satellite images come in, it compares what it's seeing now to what it expects to see. If there's a major difference, it flags it as an anomaly. But, and this is the crucial part, COLD knows a single weird data point isn't enough. It has to see a persistent, consistent pattern of change to confirm a real disturbance.
So, how persistent are we talking? Well, the magic number is 6. An anomaly has to be flagged in 6 consecutive satellite images before the algorithm even begins to take it seriously. This is how it filters out all that random noise. And it doesn't stop there. The deviation also has to be statistically huge. We're talking a 99% probability that what it's seeing is a real change, not just some random fluctuation. The algorithm is basically built to ignore the chatter and focus only on the loudest, most significant signals. And check this out, there's one last clever check. The direction of the change actually matters. Think of each anomaly as an arrow pointing away from normal. Well, COLD makes sure that all 6 of those arrows are pointing in roughly the same direction, within 45 degrees of each other, proving that it's one consistent event, not just random chaos.
Okay, so the theory sounds amazing, right? But what does this actually look like in the real world? To find out, we're going to look at some famous, really well-documented events in the Berkeley-Oakland area of California that COLD was able to see with just astonishing clarity. First up, the tragic 1989 Loma Prieta earthquake, which, as many of you might remember, caused the catastrophic collapse of the Cypress Street Viaduct on Interstate 880.
And here's what's so incredible. Just a few weeks after the quake, COLD's analysis spit out a map showing this perfectly straight line of disturbance. This is what shows its precision. That line traced the exact footprint of the collapsed highway. The algorithm didn't just see some general damage, it pinpointed a specific infrastructure failure, right from space.
Okay, next up, the devastating Oakland firestorm of 1991. This was a massive blaze that just destroyed thousands of homes in the hills of northern Oakland and southern Berkeley. And again, the algorithm from the output was just, wow. Its analysis from that time identified this huge, unmistakable patch of disturbance that perfectly matched the known historical footprint of the fire. It captured the disaster's enormous scale and its precise location. But here's the thing, COLD doesn't just see natural disasters. It also tracks what we humans are up to. For instance, take the decommissioning of the Oakland Army base, which started getting redeveloped into a commercial port around 1999.
And boom, right on schedule, the algorithm detected this large patch of change appearing in the port of Oakland. It clearly identified this massive human-driven land use change, basically watching the city evolve block by block. And for one last example of urbanization, let's look at the Wilder housing development,
a pretty major construction project that kicked off around 2007.
And here again, Cold totally nailed it. It identified the specific spatial pattern of all the new construction. This just goes to show its ability to track projects that unfold gradually, over years, capturing the slow transformation of a landscape by human hands.
So, what does all of this add up to? I mean, why is having this kind of watchful eye from space such a big deal for our future?
Well, first, let's talk accuracy. In some really rigorous testing against a whole dataset of known events, Cold correctly identified 73% of land disturbances. Now, you might hear that it missed 27% and think that's a lot, but honestly, when you're talking about the sheer complexity of monitoring an entire planet for every little change, this is a remarkable, really impressive level of accuracy. And this kind of accuracy has these huge, world-changing implications. We're talking about enabling near real-time disaster response, managing our natural resources way more effectively, tracking deforestation and urban sprawl with incredible detail, and just fundamentally understanding the health of our planet. This is the kind of objective data that can hold nations and corporations accountable for their impact on the environment.
And believe it or not, we're just getting started. The researchers themselves point out that as we combine data from more satellites, like Europe's Sentinel-2 missions, we could soon get 10 or more high-resolution pictures every single month for any spot on Earth. That would make true, near real-time monitoring of our planet a reality. Which brings us to a final and pretty powerful question. For the first time in human history, we have the ability to watch our entire planet change pretty much as it happens. So now that we have this all-seeing eye in the sky, what are we going to do with what we see?